Yeah, it's kind of a pain in the ass to get like around the headlight and down in there.
Yeah, I had a Yukon my parents have. We've pulled our bumper out multiple times because it's a steel bumper, and the car's been through a couple of car accidents, and each time the bumper came out fine. Just gotta pull it out.
Yeah.
Question why they don't make steel bumpers anymore. Those things are steady.
They're heavy.
They're heavy, but you can come out fine out of any car accident.
Oh, apparently Subaru Outbacks cannot handle the snow.
That doesn't surprise me. They also like disintegrate in a car accident. I cracked the battery in one.
Well.
Yeah. The wheel was this way. I wasn't even going that fast. Even though I'm technically at fault because I didn't follow the stop sign. I stopped, didn't see the lady because it was kind of a blank corner, and I went. And next thing you know, car accident.
Yeah.
Batteries cracked, the acid's flowing, you know. Wheels horizontal in her car. My car just had to be a bumper pulled out. And we were driving away.
Yeah.
Well, I mean after the cops, but.
Yeah, we're kind of lucky that we didn't go into the ditch on the way back to Minneapolis. Like, literally the whole ride back, it was just like...
Well, I leave for Vegas next Friday.
Driving down this coming weekend's gonna be
Hello.
actually no, so I'll be melting.
Who are you talking to?
Okay, what?
I was gonna say driving down to Minneapolis this coming weekend's gonna suck, but then I realized that it's gonna be above 30 for most of the week.
Yeah.
So it's,
Yeah,
I know.
not too bad.
I'm so happy that it decided to be warm for us to come back to.
Yeah.
Like, let us slowly acclimate back down to this.
Well, I mean, winter's kind of on its way out anyway, so
Yeah.
it's probably not dipping back down below 0 consistently again. It might hit it like once or twice, but
But I'm going to be happy to go back to somewhere warm next week.
you know.
dude, just think after this school year, I'm probably not gonna be experiencing sub-zero temperatures for a good 4 or 5 years.
Where are you going?
Or VJ.
Not here.
Good answer. Grad schools.
Yeah. I applied here, got admitted here, but I'm not going here.
It's your safety. It's your safety net school.
Yep. It's exactly what it was.
Pretty much going to pull the same thing, except I'm looking at the polymers department. Seriously though, I could not get it to work last night. Or bills.
I did figure out what was going on with mine.
What was your problem?
So I would have like my file or whatever, and then I would run like the optimization on it. So then I would just like do the same file name, but then optimize it at the end.
Okay.
And so when I was trying to do like the cube gen stuff and like the form check, I was doing it on the original files. And so that's why like none of the energies or anything like that were in there. So the cube gen was just like, oh, what the fuck's going on here? Like you don't have what you need, you know. Figured that out, and after that it was smooth sailing.
Huh. I have no
It just took a while because there's like 40 plots that we had to put on here.
Yeah.
Sorry, 30.
32.
Wait, because I thought we had.
2, 4, 6, 8. Yeah, 32.
Wait. Yeah, because we have.
20 for the alpha
Yeah,
beta,
20
and
for
then-
E, 10 for B, and then 2 for C. I think.
Alright, whatever. Well, for the last one, for this one, wasn't it 22?
I thought it was just 20.
Yeah, 20, and then like 4, 8,
12.
12.
We're having a nice debate on how many orbitals we should have.
The larger the better.
24.
Yeah, I got 32.
Super. Oh, I know the gradient. I just count orbitals and
Give us percentage based on.
yes, taking the number of orbitals as 100%. 300%, then like.
Oh, that's rough.
This color count
That's
triple.
fine, I needed it anyway. I walked in there and I told them exactly what I wanted, and then
I spent more money.
Girl.
I'm kidding. No, I had
He's like,
printing
"No, that's not what
allocations,
you
so I
want.
just
This
used
is what
that.
you want." And I'm like, no. I picked up exactly what I wanted.
Okay, thank you. Do you know how to make them transparent?
No.
The orbitals? No.
Yes, yes.
I mean, I'm sure I could figure it out.
You can try. Well, I don't care.
It wasn't part of the whole.
Sending
Yeah.
value
Oh, I have to
doesn't
put my name
depend on it, but you can just put letter.
I had to get ready to fail math
And then
this
credits
test.
will
So.
go to
Austin enough.
Hey, I'm the only C in here.
Hmm?
I'm the only C in here.
What do you mean C?
Okay, why don't we get the
Oh.
letter grade that our first name starts with?
What? No. Not even on the
B.
grading scale.
They had to invent a new grade for you because it was so low.
1, 2, 3, 4, 5.
We're missing a few people.
Well, I'm guessing Brayden is probably like us and it's coming down something worse than us.
Braden is sick, yeah.
Yeah, he was already sick. Like I'm
Yeah.
getting sick from Braden. I'm
Because
And Austin looked like he's still very much hurting from his sickness yesterday.
okay. So
Means I'm probably gonna get sick next week.
what are we
Isn't that how it works?
what are we going to do with presentations? If they are sick, will they present through online, or someone will present their share?
Well, I guess we could just hit slide buttons and show what they wrote.
So here are the subjects in the advanced skills of Gaussian, and we need to send you. We need to send me. Oh, okay. The larger number of people, the better. Congratulations on your feeling good.
Sorry.
I was expecting that everyone is feeling cold because the weather is in transit, but so we miss just 2 people to be super happy. So Thursday, this time, this place, presentations on advanced skills of Gaussian. Complain to me in private if you do not like this distribution of subjects. The Wednesday night in the lab is the last chance to cover it together, listening from me. Wednesday midnight sending PowerPoint. Do not worry, it should be short. We don't have time to much things. And then on Thursday presenting. Next month we will not do anything with Gaussian. We will start new software. So this week is last time we deal with Gaussian, and maybe even last time for the rest of the life. There are better pieces of software. Not for the record. Questions? Okay.
It's like our condo back in Georgia.
Yeah.
I swear, we just kept on going.
So there are many good things that we are doing for the last time. It is the last time we deal with Hartford today.
Should I clap or no?
Huh? What?
Like, nothing.
No. I need to record jokes for the next time.
I just asked if I should clap or not.
Well, depending on how much do you like the subject. And prepare, I wouldn't say prepare the best of your intellectual strengths. It will not be super challenging intellectually, but it will be a lot of more than average number of equations. If you take notes, you will be exhausted. If you do not take notes, you will like, my neighbor is taking so many. So it's not a wonder that we target to get the observables, right? To compare with experiment. And if something was missed and we were not able, they are recorded. So here are the subjects that I hope to hear from you. So We are missing Austin, who is expected to talk about density of states, very important thing.
Wait, do Vijay and I have the same thing?
Not much, but see, I was not sure that you both will be available on Thursday, so there is a little overlap.
Okay, so
If more than one person speaks about the same subject, it's only a plus.
Okay.
Repetition is the core of instruction. And you're not telling from any manuals or from online, you share your personal experience, right? Because we all are literate, you can take cell phone, go to Google and get answer. You share what you tried and what success of it. And today we are missing Russell. I hope he will come to tell something about where you set correction pathway and animation of normal modes. Maybe I will have time to chat about it on Wednesday night. So, if you expect to get exhaust attack, or if you're going to get super tired at the end of meeting, or you need to leave earlier, here is the summary of what you should get as a take-home message. So here is a capital F. And those who attended physics seminar yesterday learned it from discussion between Professor Krzyzewski and Dr. Khan about that F is instead of H. Right? The difference is that there is a letter C instead of psi, right? And there is a letter S that we never saw before. Okay? And here's the thing that you would get if you go to the Google and type Hartog Wikipedia. I can't compete with Wikipedia because sometimes it tells right things. So you start with atomic coordinates. You make initial random guess of orbitals or expansion coefficients of this C. You form Fock matrix that gives you average action of background orbitals on your favorite orbital. Diagonalize Fock matrix. Plug the coefficients into Slater determinant to get the total energy. And repeat until the total energy starts getting the same number on several cycles. But on each step, you plug in new orbitals that you obtain through this procedure to form the Fock matrix that carries. So the orbitals start tracking more and more influence of the electronic interaction. There is one thing I was reviewing what I'm going to show today, and I just started looking on my notes without any memory of those, and I found one thing that is missed. I better add it now. Did you play this ping pong and tennis balls together? Or if you ever picked potatoes? There is a very important experiment. So suppose you have like 100 of ping pong balls and 100 of tennis balls. Or you have 100 of very small potatoes and 100 of very large. You put them randomly into a bucket, right? And record where they are. Now you start shaking it once, twice. What will you see after?
The small ones will fall through.
Can you repeat it to everyone?
The small ones will fall to the bottom.
Why?
Uh,
Who is guilty? Who is responsible?
gravity.
Yeah, this is too general. Your gravity is guilty for everything.
Like
Person?
person. Newton?
No, much earlier. It's a best example of, I cannot pronounce it in
Galileo?
Huh?
Galileo?
Earlier.
Aristotle then?
About right. And then the first letter is correct. Yes. How do you pronounce the word of floating in
Buoyancy?
Yeah, buoyancy. So, because of Archimedes' law, if you pack smaller stuff, there is less air, there is less vacuum between them, so they, in average, heavier, so they float down, and the bigger ones have more between, so in average density is lesser, so it floats up. But you minimize energy of the system, and with each shake, it approaches the minimum of energy. It's a very, how to say, pathetic analogy with cartoon. So with each shake, you approach closer to minimum of self-consistency, right? So they feel interaction on each other and find that the minimum of total energy, right? Okay, relax now if you do not care about taking notes. There will be nothing more, only technical details. But the notes can be useful for you later. So what did we do last time? I promised myself to do it in nice boxes, but maybe next year. So Slater determinant, variational theorem, Coulomb and exchange, get into the algorithm, into procedure for Hartree-Fock. And we already got the algorithm. I will just go into more details, how it works and where it comes from. So we are looking only on electronic part of molecular Schrödinger equation. We know that many electron wave function is composed as Slater determinant, and we know that part of electrons forms background distribution right here, and another electron, the last electron, fills this background distribution. Therefore, shapes of orbitals of one electron orbitals feel the influence of the rest of the orbitals. So when we were buying vowels, we got that we can make partial average of the background electronic interaction as they act on the operators, especially in respect to electron-electron interaction, well, and other operators as well. And many weeks ago, we got to this example where we have two one-electron equations for systems that consist of two electrons. And the same can be done for as many electrons as we need. So stuff in the brackets acts on one electron wave function. So in some sense, it is one electron equation, but the parts of the operator carries information about the remaining orbitals, right? And here is where remaining orbitals are fed back in, are plugged in each cycle when we shake bucket with potatoes. So in fact, it is one electron equation, but at each iteration, we have a feedback about distribution of other orbitals. If those orbitals are exactly literally correct, then it is a correct equation. If not, it is a little bit far from ideal, but at each iteration, it gets better and better. Which is follows from variation theory. So if you know that there is a minimum, there is ideal wave function, any deviation from it will increase energy. And if you approach the ideal wave function, we will get closer to the minimum of energy. Right? Many weeks. Just want to put it on mute. So many weeks ago, we were playing a little computers and minimizing interatomic positions, finding minimum. Now we're finding minimum of multidimensional electronic distributions. But we will be always finding minimum. Hierarchy of objects. Atomic orbitals at each site, molecular orbitals distributed over all sites, Slater determinant that combines many molecular orbitals into one electron wave function, later gives total energy of the multi-electron system. Right? And the only thing, atomic orbitals, molecular orbitals, and expansion coefficients. This expansion coefficients is the only thing that we can vary. So we will apply variation principle so that find optimal set of orbitals that would help to find multi-electron wave function. And this mean field This is two words that must be near and dear to the hearts of physicists. Mean field concept is that there is a background of all but one electrons that create mean field for the last electron. But we do not know which electron is the last. And if you swap and consider another electron as the last one, the rest of electrons will create the same mean field. Okay? And those are cube files that you have just submitted as a homeworks, right? Whew. What is exchange? Not currency exchange in the airport, exchange in computational chemistry. I don't care, you don't need to answer me, but be ready to answer it to someone else. Some of you are done with your travel to conferences and some of you are going. So if your colleague on APS catches you, what is exchange? You should come up with an answer. Yes? No? Exchange of what? We are talking about what? Electrons? So exchange of electrons, right? And exchange is a part of inter-electron energy, right? Which in the context of our course is composed of two parts. One electron repulsion, which is positive, and another term into the energy electron exchange, which is negative. It stabilizes molecules. So it follows from the Slater determinant. If you put Coulomb operator between two Slater determinants, which are big many electron wave functions, you see that there is from anti-symmetry, there are negative terms, and they will give negative contribution to energy. So there is yet nothing new. We are just repeating of what we've done before. What are those funny pictures?
They look like oscillators.
I am very curious about opinion of Alisa.
Oh, I just, we've done this before, didn't we?
Yes. we are doing review. Nothing new is now.
Okay, it's the electrons and then the exchange of the paths, basically. Isn't that what it was supposed
Well,
to be?
once there is the repulsion, once there is the exchange.
Yes. And sometimes these pictures become even more funny with some loops and bubbles. Who designed them?
Fine.
Yes.
Yeah.
So we just
You get a
Feynman
Nobel
and-
Peace Prize for it.
So one electron repulses with another, and here they do practice exchange, right? And figures are much more pleasant and funny than equations. So it's still review, nothing new. We covered this one. And the next thing, if we do practice our mean field approximation, we have a background. All but one electron serve as a background. And these Feynman things are for two electrons. We do not have second in our math, in the math that we want to solve. We want to solve equations for one electron. So we need to do something with the second, and third and fourth. So we do average about the distribution of second, third, fourth, and other electrons, right? So we can do it in the following way. Put a box so that we average any possible position, momentum, distribution of second electron and just calculate average mean field force exerted by second electron and the first. So if I didn't mess up, there should be a box. Yes. If you read literature created by developers of Gaussian, you will see a term density matrix in application of Hartree-Fock, which I think is very not needed there, but they like to call pairs of orbitals of which average has been performed a density matrix, because there are different pairs of orbitals from the background. So only the first electron we are interested in, it experiences average force from the rest of electrons, repulsive. But we can do the same stuff for the exchange. So non-coinciding, but during the interaction they swap. But still, although there is a swap, we can make an average over this path of electrons, and it will mean that electron that we are describing is exchanging its identity with one of the electrons from background, and therefore energy stabilizes. So if I didn't mess up, there will be another box. Okay? So two terms, Coulomb exchange. About now, we should go to actual new material. Any questions about the past material? Anything that makes you especially unhappy? Or especially happy? Nothing. I can imagine you exhausted with other classes or multi-dimensional list of tasks for the hardest interval in life, which coincides with undergraduate studies. Later it will be easier, I promise. So actually we begin the lecture number 14. So Hartwig is the one who didn't took into account Slater determinant exchange energy. Other than that, his theory is super and very pioneering. So all components of mean field, multi-electron reduced to one electron problem was there. And I cannot tell much because I just pulled it from Wikipedia. You can do it yourself. The folk who did the same but with taking into account of antisymmetry and this stabilizing factor made the theory better. So as you have seen from your numerical experiments, it is yet far from coincidence with many molecules. It typically overestimates gap energy, and but qualitatively it is a big breakthrough. So my best connection to Fogg is that his graduate student was my undergraduate teacher in 1994. I wasn't listening much, I was enjoying life, but there is a little bridge. And of course he was a little older than graduate student age because of sickness. Well, exchange. We know all this background. Okay. There will be, the goal is to get a protocol that we can advise the programmer to build a Hartree-Fock core. We are not mathematicians. We are practical guys who need to solve something for real molecules. And real molecules consist of real atoms that have their atomic orbitals. So we are going to take it into account and speak not about abstract Hartree-Fock equations and solutions, but about practical solutions in the basis of using specific basis. So you cannot talk about solutions with abstract continuous functions. Even if you can, it is not practical. It is much better to, instead of continuous function with many grid points, to take basis set and then discrete list of expansion coefficients. Okay? But first we need to choose a basis. Some of you will, Russell is not, I'm not sure if he will come on Thursday, but I hope that he will come and tell something about basis set. If you are playing with Gaussian and Gauss-U, you know that you select basis set, and there is a nomenclature. There is different ways of basis set. So it is a way how atomic orbitals, S, P, D, F orbitals, are represented mathematically. How many of them, and there is a big secret. Gaussian doesn't have atomic orbitals. It is there is something instead of them. For human eye, it is the same, but mathematically those are different functions, which are better to process. Okay. Also, there is today is the last week we deal with Gaussian, with Hartree-Fock, and when we deal with isolated molecules only. Starting from next week, we will look much broader to the world that consists of solids, liquids, gases, and extended systems, especially periodic solids. And in such classes of materials, atomic basis set is not always optimal. So if some structure, like in crystal, repeats again and again, one needs a function that periodically repeats itself. So if you were exposed to physical chemistry, you know, plane wave is something that is periodic and matches well periodic simulations. So for atomic basis functions, you have position of atom, you have how far your electron is set off from position of atom, and then you expect it to be like a cusp, right? Here is position of atom, here is position of electron, and it goes exponentially, right? If it is on another atom, it will be same function but in different positional space, right? And if it is a p orbital instead of s, it will be multiplied by offset from the center of atom, right? And I'm forgetting about the radial stuff. So this Gaussian is multiplied by offset, therefore it gets this shape. Right? So for p orbitals you have nothing on the center, and then there is a modulation to have this two petals, or simplified flower. And for the plane wave, just oscillations. So what Gaussian? Oh, why Gaussian is called Gaussian?
Because it looks like a Gauss curve.
Huh?
Because the curves look Gaussian.
Curves what?
Like you were just drawing there.
But those are exponential functions.
Okay.
E to the power minus first. And you know that the mathematician Gauss was living like 300 years ago. He was not able to be author of Gaussian software. Any thoughts on the connection? So this function has a sharp cusp. It is the derivative is infinite in point zero, right? But if you care about chemical bonds, you're not much worried. If you're not a nuclear physicist, you're not worried much about what is going on in the tiny vicinity of nuclei. You don't care about this region. So something in the near vicinity of nuclei is not your primary focus. And there will be not much, not much error if you build a Gaussian function that will approximately mimic the first order exponential in the tails and will diverge in the tiny vicinity of that. So this is a trick. You avoid discontinuity of first derivative, and all matrix elements, all expectation values with Gaussian function becomes so much easier to compute. So Gaussian software is called Gaussian because atomic wave functions are reproduced in terms of Gaussian bell-shaped functions. Okay, makes sense? It's a little secret, but we are not going to use it today. Today we are just going to use any basis functions named with letter chi. Okay. Right. Second power. What is our focus? What in this big building, big structure of Hausdorff theory, what we can change and what we must change and what we can optimize? The hint is on the board. Letter C. Yeah. So we need expansion coefficients that tell us how much of given atomic orbital contribute to a given molecular orbital. So we need one index for atomic orbital, and it is a super index that includes position of ion, principal orbital magnetic quantum number, and second index is number of molecular orbitals, like LUMO or HOMO or something else, right? So each of molecular orbitals is expanded in basis of many atomic orbitals. Conceptually, we are almost done, but most of equations are waiting for us. No one needs to live literally at 11:50. No one wants to lie and pretend, oh yeah, sure, I'm tired of this. Okay, so we already heard this. And you heard this as well. So you have heard about all these tricks about background field, mean field. So background electrons affect on our primary electron of interest. And this primary electron of interest has its own kinetic energy, interaction to nucleus, and interaction with pool of the rest of electrons, with background electrons. Kinetic, nucleus, and interaction with the rest of electrons. Coulomb, repulsive, and exchange attractive. So we make a summation over all but one electrons. So it interacts with all electrons except itself. And this is letter F, Fock operator, which acts formally, mathematically acts only on one electron, first electron, one electron of choice. Right? One electron operator, kinetic, potential, and interaction with the rest of the electrons. So if it is one electron operator, we should be able to formulate the F and phi 1 R1 equals E. So with Fock operator, we can find molecular orbitals. Right? No wonder. We were preparing for this glorious moment for several weeks. But now, if we you're not satisfied with just writing a nice introduction and method section to the paper, if you really want to help a programmer to program the code, we need to recast this equation, taking into account that we already have a specific basis. So we need to reformulate this equation in basis, in specific basis. So right now, those are abstract mathematical concepts, but if you go from continuous wave functions and abstract operators to a basis, then each wave function becomes a vector, and each operator becomes a
Matrix.
yes. So how to make this a vector, how to make this a matrix. You'll see it's just little note on the side that you'll see very soon. Since, well, atomic orbitals are orthogonal to each other if they are sitting on the same atom. But if they're sitting on different atoms, there is no guarantee that they will be orthogonal. So this basis set is not orthogonal. So it is, in some sense, it is bad basis set. So some orbitals are not orthogonal. In this measure of non-orthogonality is this overlap matrix. So orbitals sitting on different atoms overlap. And they're neither 0 nor 1, something in between. And we need to take it into account. Notation, general notation. You saw it. Okay. There is a Fock equation, one electron equation for molecular orbital, and we need to cast it in a specific basis. How do we do it? So we write that this phi is expressed as Ci nu chi nu. Right? Atomic expansion coefficients, and then you plug in this orbital here and there, and nothing changes. But we do not need the atomic orbitals. After we plug it in, we can do the same trick as you may have practiced many times in quantum theory. If you have equation with wave functions, and you want to get rid of wave functions, you multiply everything by orbital conjugated with different index and integrate. Right? Two wave functions convert into number. Good or bad, but number. And we get rid of wave functions and have only numbers, only vectors and matrix elements. Right? So two numbers and matrix elements. Numbers and matrix elements. You agree? It's a main trick. Not trick, main step. You already have all philosophical background. This is main practical thing, and the rest will be just a couple of boring mathematical steps. But you already have Hartree-Fock theories encoded in your heads. The rest is processing. I can stop, finish, and you sit alone and derive the rest. Your education allows you to do it. I'm confident. It's really, well, it's exhausting. It will take you maybe longer than an hour, but it is possible. So here is what we get after we plug in wave functions as expansion over atomic orbitals. Yeah. Atomic expansion coefficient. Atomic expansion coefficient. We haven't yet. Last time I used letter phi, it should be letter chi. Chi mu. R1 star integral dr1. So we need to apply this stuff to left and right sides of equation. Right? So if you do this to left and right sides, you'll get the chi star and chi will kill each other. Maybe kill each other. And here, when we process the right part of equation in a good quantum mechanics, multiplication of wave orbital star and orbital itself will get either 0 or 1, and equations will become super simple. Here we do not have this luxury. So instead of delta function, we will have S matrix. S means overlap matrix. It will carry the information that orbitals that do not sit on the same atom overlap strangely. Not 0, not 1, but something in between. But it is a matrix. It is a collection of numbers. It is not an operator anymore. So we get rid of atomic orbitals. If you process so it is what is going on the right side. On the left side, if you put this stuff here, and integrate, you'll see an object that you started liking 2 weeks ago. Operator, orbital on one side, orbital on another side. If it would be a general wave function, this will be expectation value. But if those are eigenstates, and it is not an immediate observation of anything, but it is computed same way as we compute observables, the name for this thing is, so it will be matrix with indices mu and mu. It is a matrix, and one word is missing.
Element.
Yes, matrix element. Do you recall it from CHEM, more or less? So matrix element of Fock operator. Okay. So on the left, we develop matrix element of Fock operator. I'm just lazy to write the whole word. And on the right side, we will get overlap matrix. So matrix element of overlap. So I will show this how it develops in form of equations, but in fact you already have it. So instead of abstract Fock operator, you get F mu that acts on C nu comma I. On the right, you have unknown energy times matrix S mu acting on C nu I. And in both cases, we still have summation over mu. So if it would be regular quantum mechanics, the summation and delta function would eat each other as a snake and a rabbit. Whether it's who. And here, just matrix times vector. Questions or objections at this point? So summation, matrix element of Fock operator. This stuff is overlap matrix. And unknown, there are two unknown things. This C coefficients and energy, they are unknown. But this is a equation that we can process and solve. Right now, finally, we come to the sort of equation that we can solve. It will not solve the whole Hartree-Fock problem. It is only one step in this self-consistency procedure, but it is a solvable equation that mathematicians like, and the amount of basis functions. Suppose you have 300 atoms, and maybe 100 orbitals on each atom, or maybe less. You'll get just few thousand bases, and it's like matrix 10,000 by 10,000. To diagonalize by today's laptops, it's nothing. And with clusters, supercomputer clusters, it's regular task to diagonalize matrix 10,000 by 10,000. So you could become happy by now and thinking like, okay, enough because I understand everything, or enough because I'm tired. But let me do the following in public. Let me convert this expression, which is correct but not nicely wrapped, into something that may click and make you happy, if equations may make you happy at all. So we are solving diagonalization problem, and we are talking about diagonalizing matrix, finding eigenvector. So where is the matrix? How does it look like? There is no trap, there is no trick. It's a trivial question. Just rewriting this equation in a better form. So, yeah, nothing new. So if we call this Brian cat matrix with two indices, it's also two indices, and this is vector. The notation of two index object with summation multiplied by one index object is a shorthand notation for row by column rule. Right? If you do like A, B, C, D, X, Y, right? So while you're going through different elements in a row, a column index in a matrix, and when you go through different elements of the different rows in a vector, this is the index new here and there, right? So we go this time, this time, this. It's same as summation over index. It's same. First, second, third here. Well, the remaining one stays untouched. So if you see object with two indices multiplied by object with one index and summation, you can immediately say, oh, it is matrix by vector. It is always the same. So if you see this notation, you can unwrap it back into the matrix times vector. So the matrix will just coincide of F sub 1, 1, F sub 1, 2, F sub 1, 3. So F matrix element with different indices. And the vector will consist of this C. C sub 1, comma I, C sub 2, comma I, where I is number of eigenstates. Okay? Give me a little sign if you do not feel super comfortable with this notation, so that I just do not become too happy. No? It's okay? F 1, 1, F 1, 2. I'm lazy. F 2, 1, F 2, 2. Matrix times C1, comma I, C2, comma I equals E sub I, because there are many solutions. There are several eigenvectors and several eigenvalues. C1, comma I, C2, comma I. So, what is wrong? S is missed. S is missed. I'm too excited and under the pattern of what happens in regular point of view. Yes. we should have the S 1 1, S 1 2, S 2 1, S 2 2, and here we do this C1, I, C2, I. Yeah, thanks for helping. Thanks for catching. So one matrix times unknown vector, second matrix times unknown vector, and unknown energy, right? So it is Hardy-Fock equation in a specific basis. Hardy and Fock didn't focus on this. It was another scientist. And I always do mistakes in spelling the name. So it is, I do not remember how many O's and how many A's, and how to pronounce it. Ruthan, but it is a Ruthan equation, which is Hardy-Fock one-electron equation in matrix form. But it is what is being solved in the Gaussian software and any other software where Hardy-Fock equations are implemented for quantum chemistry. So it is diagonalization. Now, just a little addition for a bit more comfort. Two matrices are too much. Typically, when you diagonalize matrices, you have just one. How to get one matrix out of two in this case? You can just subtract them one from another, right? So put 0 here, vector of zeros, and here write f minus epsilon I sub S11, F12 minus S12, F21 minus S21, F22 minus EI S22 equals 0, 0, 0, 0. Okay? You follow it.
Is there a reason that you weren't including the energies on the off diagonals?
No, you should include the energies of diagonals. You're correct. I'm under standard pattern that energies must be under diagonal. So it is same what we did. So vector of unknown expansion coefficients, or second index just number of eigenstate, and we can, instead of writing this vector all the time, we can just add the little arrow that symbolizes vector, right? And then we can formulate Fock matrix, overlap matrix, and merge them together as we already did. Translate Fock equation into matrix form. Ruthan equation. Well, for several years I'm not able to, and here I try to do it indefinite, either 1 or 2 A's. And if we use the fat symbols or calligraphic symbols for matrices and vector symbols for vectors, then so the Fock matrix times vector of unknown coefficients equals unknown energy times overlap fat matrix times vector of unknown coefficients. And then, thank you, Alan, for good eye, just multiply and subtract. Non-selectively, all elements by unknown energy. And then you know that in order to diagonalize a matrix, you need to find determinant. But it is not our problem now. We will hire someone who will diagonalize matrices for us. We just need to formulate the equations. And as soon as one diagonalizes, one will find set of energies and set of this expansion coefficient that help to unroll back and by multiplying atomic orbitals to get these shapes of atomic orbitals. So when you see the check file, it doesn't have these shapes. It has only information about expansion coefficients. But when you do form check and then later cube gen, it unrolls it back into the shapes, multiplies by atomic orbitals. I don't know if I have more slides. I do like whatever I want. It will be a surprise. You saw it. So, bucket with potatoes. Small on the bottom, big on the top. You repeat it in a cycle-wise until it converges. So you formulate Fock matrix, including information about shapes of your orbitals that you, at the first step, you guess. On the second and subsequent iterations, you plug in this expansion coefficients to formulate Fock matrix. Right? It includes information about the background of orbitals. You diagonalize it. Here it's skipped. You find total energy and see if it asymptotically converges. If yes, you go forward with finding observables. No, you repeat. So from now on, you are entitled as certified experts in Hartree-Fock theory. I don't think we need to invest time into making exam on to check how good experts you are. Let's trust that you already are, and make our efforts on practical aspects, on the actual preparing input, analyzing output, and making educated operation of Gaussian software for Hartree-Fock and other methods. I believe now it will be my favorite slide. Yes. Thank you much for staying. I will stay here for any questions and hope to see all of you on Wednesday night for last lab before presentations. And some of you who are involved in research are welcome to join another meeting this evening. Just 1 hour. You were quick. Hartree-Fock theory in 1 hour.